Welcome back to the Wireless Village. Ha! Like most of you ever left. Contestants, I'm sure you remember by now, but please be quiet. We're all very glad you're here. And quiet. Really quiet. Because I don't want to have to take points away or drop this mic. So, it is my distinct pleasure to introduce two people that, well, if you were playing the dog collar game, you already know. These are two of our newer friends of the village. They've managed to ingratiate themselves in a short time. Tim was one of very few people who said, dog collar challenge, that sounds like fun. When Russ first introduced it, no one else would play. And then after Tim played for about 45 minutes, nobody wanted to play against Tim. Yeah, that's been a lot of fun. He had no idea how software-defined radios worked right up until then, and then he's been ruined ever since. I'm sure he does nothing else from the look of it. And Woody sent me, I cannot even imagine, the most entertaining email I have ever read for the CFP. Something to the effect of, I'd like to give this talk, but I need to bring my dog. Is that okay? I'm like just bringing your dog. Is there any particular reason? Well, it's a hearing ear dog. Okay, sure. So it's actually a service animal. It's not like a service pony. It's a dog. Yeah. Okay, yeah, you can bring your dog. No problem. So these are some of our newest friends, and they have done something that the entire Wireless Village team wanted to do, which is reverse engineer the bloody Gotenna. So I present Gotenna Reverse Engineering with our new friends, Woody and Tim. Woo!
So we're glad to be here. Actually, we want to thank Wireless Village. They also gave us a chance last year at DEF CON. We presented Iris for any of you that have heard of infrared and how that might be a way to track cell phones. We did that. They gave us a chance to do that, and they brought us back again. So pretty happy to be here. A little bit about me. I go by Woody, and I play with software-defined radios and RF, and now Tim.
I'm Tim. I came here to the DEF CON for the first time about 3 years back and got really excited when Russ was playing with dog collars. It's like, man, this is going to be fun. Not only can we shock people with dog collars, we can set this thing up on the internet. Japan's going to get really excited about it. Anyways, so we're going to be working on the Gotenna here. This is something that came out a couple of years back out of Hurricane Sandy in New Jersey. There's two people, Daniela and Jorge Perdomo. They're siblings. They thought, it'd be kind of neat if we could have some way of communicating when cell networks go down. And so they made these things. Do you got one on hand, Woody? They're about the size of a pack of 6 pencils kind of taped together. They're really small. And you pair your phone to it over Bluetooth. And so once you've got your Bluetooth link up, we got one over there. Pretty sick. Anybody else in the audience got one? Anybody else? All right, well, we actually have a discount code from them at the end. We don't work for them, but we ended up having to contact them about something, which we'll talk about later. So anyways, you pair it with your phone or Bluetooth, you send a little text message to your buddy, and it goes out over MERS, which is sort of similar to push-to-talk radio networks for family radio service, things like that. And so some expectation management for the talk. We're not doing anything with Bluetooth. We're not doing anything with mobile applications. It's just not our skill set. We're going to be focusing on the MERS link and how it communicates. Also, Gotenna is coming out with new hardware. This is not the new hardware that we're studying. We're studying the older classic hardware, if you will. So.
Now we have ordered the new hardware, and hopefully it'll be arriving within the next few weeks, but Gotenna is a fund me thing, so we're waiting for the new stuff to come out. So a couple things we're going to talk about. We've all heard of this OSI model. What became interesting as we did this, a lot of things we do with software-defined radios, key fobs, entering vehicles, bypassing your home alarm system, being able to open your garage door. I don't need to worry about the OSI model as much. Pretty much I have the hardware, I'm able to collect some stuff, I can replay, make a couple changes, and make things happen. That wasn't the way that this worked. This actually has networking. This actually has the physical model. This actually has presentation, sessions, and applications. So I had to read. But fortunately, I had Tim, and he reads much better than I do.
So go ahead and tell them how we got started.
Screen's blank. Okay. So here's how we got started as he pulls up the presentation. So this is what we did as we first started out. I got excited because I'm a big fan of using software-defined radios, and let me caveat with saying that if you broadcast on the MERS network without permission, that is an FCC violation, so I'm making sure to tell you don't ever do it. And if you do it, only do it in the casino with a Yagi. But with that being said, in my own home, on my own large piece of property, inside of a RF-free Faraday environment, I might have played with this. So, as I did that, one thing I noticed is I could replay a message from a Gotenna device hours later and have another Gotenna device still accept the message. So I was like, oh, that's kind of interesting. That would be something that could be of use if I had done that. In a perfectly Faraday cage with no RF environment or anything else. Yeah, my ferret cage was good to go, so I was fine. So the first thing I did was I started looking at a spectrum analyzer because I called Tim. I said, hey, this is pretty cool. We need some really high-end expensive equipment to be able to move further with this. So we used Osmocon FFT. You're going to find out throughout this talk, we want to promote you to use basic tools and be able to use simple tools to do complex tasks. Osmocon FFT. So I invite Tim over and I'm like, hey, I know that you can do some rebroadcasting with this, so let's figure out how this thing works. And Tim is really good at software-defined radios, and he can write some really cool code. So he said, okay, well, let's start playing. And there, boom, things start hitting. So can anyone tell me what's happening right here? The biggest thing you take out of seeing here? Exactly. There's a command channel, obviously. So you see where it spikes right here?
No, hold on. How long did someone say command channel? That took me like 20 minutes to figure out. I didn't believe them.
Yeah, so here's what happens. We sent about that many packets, and I go, hey, Tim, look, they got a command channel. And he's like, no, we're going to have to do some more tests. I said, no, that's a command channel. So Tim can write really well, and I can kind of look at weird things, and sometimes they pick up. So I was like, I think there's a command channel at the highest end, because we knew there were 5 channels. Why? Because FCC's our friend, and we knew there were 5 channels in the MERS band. You're going to find more out about that later. So Tim doesn't believe me. You'll find out if you were here for our Iris talk. Tim's a firm believer that I hunt unicorns.
He does.
I will tell you, unicorns are real. So what happened after we started testing this out? We realized that they're bouncing around, but one thing stayed consistent.
So being a little bit more of a scientific man, I thought, hey, how can we test this and actually prove somehow that there's a command channel? So if there's a command channel, what would that mean? That means there's some sort of trunked radio network. And I said, well, let's do something that I think will help Woody and I understand this problem. So I said, Woody, let's start role playing. And so I put on my robe and wizard hat. All right. Woody's going to be one Gotenna. I'm going to be, yeah, he's really into this, by the way. He made a character, maxed out the stir and int, and I maxed out my whiz. So it's just kind of, yeah, there you go. Lightning bolt. Anyways, so I'm going to pretend like I'm trying to talk to Woody. I'm one Gotenna, I'm the other. I'm going to start on channel 4. That's the control channel. I'm going to say, hey, Woody, I want to talk to you. Let's meet on channel 2.
Now, Tim didn't do this to try to make it prove that I was right. Tim was like, well, I'm going to show you why this doesn't work. So Tim said, we're going to do this, and you'll find out if it still bounces around, Woody, you're wrong. Because it's free cop, and I don't think there's a command channel. I was fortunate enough to be able to say, well, I think there is. So we did it.
What happens if you're on channel 2?
Yeah, so what happens if we start sending it to where one radio is off, and we send, and that radio doesn't authenticate? If there's truly a command channel, it should only send from one channel over and over and over. So let's reset our peak holds, and we're going to shut down all other radios except the one who's sending. And if what we're saying, oh, by the way, we're doing this live demo because if we're not willing to go live, should we really be here? We have backups, but I think there should be some principles.
All right, so we're all the way off. I've got my phone on, and I've got my Gotenna on, and I'm going to try and transmit to a Gotenna that's currently turned off. If Woody was right and I was wrong, what we should see is on channel 4, that's the one all the way on the right, we should see it talking and never hopping over to channel 2. To finish off the conversation, what was supposed to happen is, hey, Woody, let's meet on channel 2. And Woody was supposed to go, okay, Tim, I'm ready to receive a message, but he never did that.
So if it doesn't have a command channel on channel 4, it'll bounce all over the screen. So, God dang it. I'm sorry, Tim. I'm right. So, now I might be right, but he can script, so he wins. But still. So, as we started to look at this, we were like, dang it. This could be something to look at. Because remember, if I know where you start, what are you probably going to tell me when you start? Who you want to talk to and where we're going. Woohoo! So we start working. So let's go ahead and tell us why the FCC is our good friend. We were able to find the actual board on the FCC. Why? Because they have to be there. Now, as we look at this, remember Tim told you we're not doing Bluetooth exploit, not even going to attempt it. However, in the lower left-hand corner, that is the Wi-Fi antenna. I'm sorry, Bluetooth. We're not using Wi-Fi, please. Okay. Case of beer, got it, understood. Now, as we move up on that whole side, we look at the protocol and we realize that we move over all the way to the right. That is going to be the MERS antenna. And if we come just between everything else, that is the actual radio antenna for the Gotenna. Now, this is the antenna, which for MERS is fairly small, but it's one of those things they're working on. So at this point, we're like, okay, we're looking at this board. We're able to find some information. So what kind of modulation do you think we're going to use, Tim?
So this is going to be on the MERS channel. So if you're familiar with push-to-talk radios and that whole plethora of frequencies that the FCC allocated for unlicensed people to use, everyone's using frequency modulations. So pretty sure about that. It's frequency modulation. And also on top of that, it's probably going to be within a 12.5 kilohertz channel because each of the little push-to-talk radios, every time you go to the next channel, 12.5 kilohertz. So I'll show you the modulation.
We should probably go to a live demo at this point. So why we talk about this a little bit and we wait for this to pop up, there we go, wait's over. We looked at this and we're like, okay, it's probably, Tim's like, hey, you know what? I bet they're using FM. We'd seen a few things that made us feel that way. Then we looked at the FCC stuff and he said, hey, let's really sketch this out and see how it works. So let's go ahead and send something and see what it looks like. Now, there we are. So we have a good amount of data here. For those of you that are familiar with FM or frequency modulation stuff, you realize it's a little different than on-off keying, and it can be a little more difficult to demodulate and see what's going on. So we need to figure out where all the packets start.
Why would you use FM over AM in an emergency?
There's questions coming at the end, sir, but I appreciate your enthusiasm. That is a great question, and please remember at the end that we're willing to answer those. It's okay.
I'll try to remember it. Somebody else remember it for me.
Yep.
All right. So one of the interesting things about this one is if you look at these bits that are being transmitted, they're not square. If you're looking at a doorbell or you're looking at a wireless fan remote, they're going to be square because they're pure FM. They're hopping right between two frequencies. As soon as that bit changes, boom, just hops right over the other bit. Problem with that is it makes your frequency content really wide. And if you are here for Balin's excellent talk, when you start increasing your bit rate, you start increasing your bandwidth. And this is something that we're under a constraint from the FCC. So what you do is instead of hopping instantaneously between frequencies, you slide between frequencies. That lowers your spectral content. As you can see in the bottom, that's only about 9 kilohertz wide. Easily fits within 12 kilohertz.
So as you look at this, and remember, Tim's the person who taught me software-defined radio, so anything I say incorrectly falls on him. But Guzman modulation is what we're looking at, and I'm sorry, Gaussian. But the way this works is it helps us know that it's something else that we need. We need that because we need clock recovery. We need to be able to figure out the timing, the sequence of these bits to be able to turn them into ones and zeros. And then from those ones and zeros, we need to be able to make real information.
This part of the packet's called the preamble, and it's something that most radios like to do to start out. It's kind of like, it kind of gets everybody's attention, but it also lets the clock recovery algorithm sync to each bit. So what you're looking at here, I'm going to try, I'm getting a little fancy here. Let's see if this is going to break everything, stem plot. All right, those are the actual samples. So if you had an array inside your programming language, each of those would be a sample. The problem is we got to figure out which one is the one, which one's the zero. So this is where something that really handy came in from Andy Walls.
Andy Walls, the stuff that he did. Oh, by the way, this is all GNU radio based, which means everybody has a chance to play with this. You don't have to be high-end or anything else. You don't have to be some guru. Everybody has an opportunity to play with every piece of this, and it will be released so everyone will be able to do exactly what we do up here, even noobs. Now, we got bad clock recovery. So, Tim, tell us what that means.
So if we have bad clock recovery, it means we're not going to know what bits are correct inside our packet. So you can see here we had 10101010 in the preamble. We shouldn't see that sloping. This was the stock clock recovery block in GNU Radio. Don't make me say that again. So it didn't do a very good job. The one that Andy Walls wrote was much better. You see how each of those points are pretty much perfectly on plus or minus 1? That's great clock recovery. And for these longer packets, these variable length packets, we really needed to have something that would be good on that. So thank you to Andy Walls if you're hearing this.
Now, one of the other things that needed to be done was a way to actually look at this and spit it out into something that was readable, where you could actually start and stop where you wanted to. So Tim came up with this really cool module for GNU Radio called GR Revenge. Now, let me give you a caveat. You're going to have to use that when we release this. You're going to have to add that to your repositories and everything from GitHub. When you look up GR Revenge, what's going to pop up is Girlfriend Revenge over and over, because that's apparently the #1 search for Google under GR. That is not what he wrote. It is GR Revenge without an E, so please find that on GitHub. It will be an issue. I promise you when you search it, that's what's going to pop up. Now, what we're able to do here is take the information, start with a radio, move it over, and as we set it up, because we know there's 5 channels in the MERS, right? We break it into 5 channels. Not we, him. Okay? Now, we break it into that and we make virtual syncs. The virtual syncs give us the ability to now continue working our progresses and see what each channel does individually. So if we can look at all 5 channels individually, we can start figuring out how they work together. And because we've already started to figure out there's a command channel, the command channels tell me where the next place I need to look at anyway. And once that happens, I can ignore the other channels altogether.
So just to run through this really quickly, it looks really complicated until you start doing FM demodulation enough, and all of a sudden, once you do it enough, this becomes like this design pattern that you do over and over and over again. On the far left, demodulate it from a radio signal into something that you can plot out on an oscilloscope. After that, you do a low-pass filter on it to make sure there's less noise. Clock recovery, turn it into a bit, 1 or 0, and then after that, look for the packet. So we had to figure out what the sync word is. This is a stream of information coming through. It's not, there's no way to slice it up easily. So as far as radios are concerned, they have to know when a packet begins. So what they do is they shift every bit they think they're receiving into a shift register, and they look to see when the shift register equals a magic value. In this case, it was 2DD4. And when we found that, we weren't actually sure if we found that correctly, so we Googled it, and we found the data sheet for the Silicon Labs radio, which turned out to be really good.
Now, one thing, as you look at this and realize spitting the data out and being able to see it, one of the interesting things that really came out that Tim found, which should really go on his counter, but he didn't put it on here, is the fact that as he comes through and he's able to spit this data out and be able to see what's going on, he does a great job because initially we didn't know the full length is, remember, we've got a lot of information. We've got back and forth like a Wi-Fi handshake. Initially, we didn't realize we actually have to be able to segregate the length of the packets for every step of that communication. So now we start looking at this. And initially we're like, oh, 11, we're good to go. We know how long this packet is, right? Yeah. Yeah, so we had some issues with that. That may not have been correct. So then we come down here, we're like, oh, well, things are looking a little bit better. Now, if I want to start figuring something out, I know that I have a protocol that uses encryption, but I also know that the same protocol can be used without using encryption. What's the first thing we do to start checking ourselves? We send information unencrypted, and can we find it inside the packet? Oh, Scheitzeville. So there's 41, which would be a capital A, 62, which is actually a lowercase b, and then 63, which is C. And we had just sent that exact same message. And right next to it in red, it actually gave us the length of the message. So if we can transfer this over to the encrypted side, we can start developing how long the packets they're sending are. Now we start looking at everything else and we start realizing we can count how far it goes to start figure out a little bit more information. Yep. Eat the elephant one bite at a time. Now, you see the 1E up there? So as we looked at 1E, what we realized when we upped the size of the packet by 1, it now became 1F. And Tim informed me that means it went up by 1 size. So I was pretty happy because we had now done A, B, C, and D. I also watched Sesame Street a lot, so I was like, this is probably the system we should use because that's what I watch every day.
All right. So I had to tell Woody, though, that the next thing after 1F was not 1G. It was actually 20. All right. All right, this is another one of Woody's wins. I'll have him run the slides for a little bit here. So one of the things, he called me up on the phone. He was really saying, Tim, I just found the next channel they're transmitting on. It's this bit right here. It says 2, and then the next channel it transmits on is 2. And I'm like, they could have put those bits anywhere. This could have been anywhere inside the packet. And he was just so dang certain of it. And I'm starting to try and learn from my mistakes of telling Woody he's wrong every time he's actually right. So that's how I remember it going. Anyways, if you look at that one that's highlighted right there in green, the 2 tells you that the next packet is going to go on channel 2. And on the second one down here, the 3 says it's going to be on channel 3. Turns out we didn't need to know that. In a single receiver system that can only look at one channel at a time, it's really important for it to tell the next radio, hey, I'm going to be talking to you over here, you need to go there. But we're looking at all 5 channels simultaneously. So although we found that, it's just a interesting thing to know. So yeah, I'll give Woody another point for that one. And so we found the length of the packet, right? This is starting to tread into like layer 2 territory. So an Ethernet frame, a lot of times this is who it's going to. It's got a length, it's got a payload, and then the checksum. So we're starting to step into layer 2 territory. We found the synchronization, we found the length byte, where it's located in the packet, and we found out just about enough to start trying to find checksums. This was really hard. And without a checksum, we're just going to be looking at a bunch of bits on the screen. And this is really hard to look at and figure out who's talking to who. I don't even know which radio it is. We have no checksum. If there's any noise, we're screwed. So that was kind of me. And I came in one day and I found Woody just sitting there with a screen with packets scrolling across them. And I'm like, oh, hey, did you Dremel the thing apart and solder down onto the debug wires and write some thing to analyze the packets? And he's like, no, I just plugged into the USB port and it showed up as TTY USB. I mean, I don't even know why I wrote this whole radio thing. Yeah, so he also introduced me to Dumb and Dumber. I'm a nerd, I don't get out, I don't watch movies a lot, so this movie's actually really funny. Yeah. So 1.440. So we actually got full packets here coming through, which meant we didn't have to worry about the checksum yet. That was just something we pushed off into the back burner while we worked on it later. I'm going to pass this off and let you talk to the next one.
Okay. So what was interesting about that is Tim had been working this clock recovery piece, and he's like, man, I think I really got this, but I can't confirm it. Well, now we were able to actually, from the radio, see what it said, and then compare his radio to it. And he's pretty good at writing. Guess what? Tim was right. We're going to keep that low, though, because then he'll put it on his column. So as we start looking at this, we start figuring more things out, and we keep getting this Gotenna ID when we start getting into the serial port. They call it a GID, which would basically be the equivalent of a unique identifier. Think of anything else. So as we start looking at unique identifiers, we keep having these numbers pop up. Now, as we look at these numbers, up here where it says TRX and you see ODB9, we kept seeing that, and we're like, hey, every time I send to somebody, it says that first where it says, hey, you on this channel, I want to talk to you. Okay, well, that works. And we start realizing that we start seeing these packets. Oh, and now let me tell you, you know how you start figuring this out when you just have a whole bunch of numbers and letters on the screen? Anyone in here ever heard of a little program called Vim? Yeah, well, I don't know how to use it. So we use Get It. So, Get It, Control F. So if you're reverse engineering something and you really want to have a quick, easy way to do it, and I'm not insulting anyone on Vim because I can't spell Vim, what I use is Get It. I take Get It, I use Control F, I highlight what I'm looking for, because part of this talk is we want to help you learn how to use the basic tools to be able to do this for the basic person to be able to do it, and for the advanced person then be able to add it to their advanced systems. But by doing that, we start searching and seeing where this pops up in all the packets, and man, we keep seeing this 5857OD FECDB. We keep seeing the #16 equals DB9. And I keep looking at that, and I'm like, Tim, I think I know what that is. Go ahead.
So we found some other stuff. There's cryptography. So it's public key cryptography as well. So at some point, I'm going to have to exchange my key with each other. So I found this in a message, public key, and it told me what it is. And then I Control F for it, and lo and behold, it's sitting somewhere down here in a transmission message. So we know they're transmitting the Gotenna ID. We know they're transmitting public keys. And that actually helped us even understand the format of the protocol, because this is 49-byte long public key. This is a 49... Anyways, if you turn 49 into hexadecimal, it turns into 31. And so we're understanding even more of this. A pretty common paradigm for sending variable length packets is you say, this is what it is. That's the first byte. The next byte's the length. Then you have your data and maybe a checksum. If you go back to this previous slide, you see where it says 01, 09, and then the Gotenna ID. 01 means Gotenna. There's 9 bytes to it. And you keep going on to find the end of the packet there. So this helped us really understand having this debug port, like the what's it called? What was that rock that they found in the desert that helped him understand Greek? Thank you. All right, so I'm also bad with history. All right. So I wrote a script that would let you plug 2 Gotennas into the same computer, and it would interleave the serial port streams. And what this meant is, beforehand in the wireless domain, I didn't know which radio was transmitting what. I just got all these packets. I didn't know who was talking. But now I know this radio started the transmission, and the next radio responded to it. So sitting up here, that's Woody's 2. He's really excited about that. And this is kind of a little obtuse to look at. So I translated it into English, right? So it starts out, the first radio is transmitting, it says, hey, I'm looking to talk to a guy, ODB9. That's like the short name for the whole Gotenna ID. It lets them get away with not transmitting so much on the control channel. The next thing that happens, just like Woody and I sort of hypothesized in the beginning, it meets over on the message channel and says, yep, this is me. What do you want to say? Well, here's the problem. If I say, I'm looking to talk to W, how many people in this room have a name that starts with W? All right, we got a couple people, Woody included. Everyone's got to meet. I actually have to disambiguate that and say, okay, I actually wanted to talk to this guy. Is that you? And also, I might need your public key. Further, the radio goes and responds. Here's your key. And then you end up transmitting the data, which here's the data from this paradigm for transmitting stuff over a lossy medium where you're going to lose a packet somewhere or get a byte corrupted, and it's like, I need you to send this again. Fortunately, we're working really close to each other. We didn't have to worry about that. There you go.
So now we start looking at this and we start going, wow. So we can see, using the serial port, when each person talks, when they want to send something, we start realizing it was almost like a golden egg given by the person that designed the protocol, that it goes 1, 0. Hold on a second. Even I can figure this one out. Remember Sesame Street? 2, 3, 4, 5, 4, 5, 6, 7. They start following it into a sequential order as they start working the packets out. And that was pretty nice to be able to figure out what's going on. And as we move to the end of it, we're actually able to see they start designing out the packets they're going to use, how big they're going to be, and what sequence they're going to fall into. And yeah, header versus payload. So we're like, wow, we can work with that. And then we come up to one of the funner nights of the entire project. This is called the GID, which we've already said is the Gotenna identifier. Who in this room's ever used the Gotenna? Anybody? Can anyone tell me what the default protocol is for using a Gotenna? For the name that you want to be, for your unique identifier? It starts with phone, ends with number. That's right. So here's the thing. But Tim and I aren't those guys. Like, we don't use our phone numbers for stuff because we both have high levels of paranoia. So we always use randomized. So this actually was a setback for us at first. So we start looking at this and we're like, man, we're never finding this 972210 in any of the data. I don't know how they're sending it. Then we're like, well, wait a minute. Maybe we look into the hex. Maybe it's some kind of MAC address formula, because obviously whoever wrote this is going to make sure it's very secure and a very high-end protocol. Nah, that ain't working. Well, let's look at it again. Maybe there's some kind of sequential ordering that goes back and forth, and we start kind of pulling our hair out a little bit, and we start going, hey, what is that? Anyone here ever use a thing called GNOME calculator? Well, hold on, before we get to that, well, no, we're about there.
Okay.
So let's just talk about GNOME calculator. So GNOME calculator, which is in most Linux systems, it allows you to take like hexadecimal and transfer it into other protocols. But we figured there had to be some high-end things being used. So this is what we did. We just jumped out of presentation mode and said, let's just get it on and just throw things on the screen.
So the thing that you talk to this
Yep.
is that
Oh, yeah. So what Tim was just saying, because again, remember, he's the guy that helps teach me. So any mistakes I make are his. So we started noticing, you know that whole 9597 sequence you saw? That's a fairly high number. But then we decided, you know what we're going to do? We're going to use one of the cell phone numbers, just like the default protocol is in Gotenna. And when we did that, we're like, wow, that's a really little number. That's a little odd. So we busted out the GNOME calculator. Again, please always use basic tools first, because then you can talk to me and I can understand it. So we throw the information in there. 0001, C3, 89, B0. Wait a minute. What? Own Scheitza biscuit. That's a phone number. Your to and from blocks we know have been identified. And what we realize is they broadcast, if you use your phone number for Gotenna, your phone number. So if any of you do open source information or technologies, we can talk on the side, but I'm pretty good with phone numbers and Facebook to be able to figure out who you are, but that's another conversation. How dangerous could it be?
last one. This is the last thing we
Oh, well, and then we're sitting there and I was like, man, I'm bored. And Tim was working on the presentation, and he's an engineer, so he like works on things like really intensely. So I get bored really easy. And I got tired of shaking my keys because they weren't shiny enough. So I said, I took a couple phones and I just started saying, well, now there is a fix for this. If you use the Gotenna GID random identifier, you know what's going to happen? You get a random identifier and you don't have to compromise your phone. So Gotenna has put this in there. I want to add, there's not a slam on Gotenna this whole talk. I still like Gotenna. I will use Gotenna, and I think for what it's designed to do, I think it's great. And I want to make sure I add that in there. But I was like, man, hey, Tim, do you think I could make 2 Gotenna IDs that are exactly the same? If they're random, at some point, they'll cross-contaminate and they'd have to be identical. And he's like, Woody, stuff doesn't happen like that. So I said, Tim's poking me again. Remember, he beats me all the time. So what I did was I took 2 phones and at the exact same time, I pressed new random identifier on both of them. And we realized this is a time sequence. Now, then I was like, well, what if we go back to, 1970? No, I don't know, maybe 1970, a certain month, a certain day, a certain time, and see what happens. Couldn't do it. We could go back to a certain date, and that's the furthest it led to go back. So we could go back to a certain date and try to set it at the exact same time, but it actually goes all the way to the millisecond, so we couldn't get the same one. I was a little bummed, but that's okay. But what we did realize is the year doesn't matter. That's what the 9 does. It stops you from having the year important, but the month, the day, the time, all the way down to the millisecond, that's how you set these identifiers. So you can, from someone's identifier, at least know some rough information. So even if I don't have your phone number, I can still pull some rough information out of this, and I can still do link analysis. Tim, those are your words, not mine. Tim loves crazy walls.
So if you've ever seen a movie where there's like some guy sitting up with like this wall with all this stuff and little red lines going there, it's called a crazy wall. And we made our own crazy wall. Sorry if you just give me a second to get it open. Pulling open my favorite tool here. I'm going to actually need to move this to my monitor so I can see what I'm doing. So what we ended up doing is one of our primary tools, like we mentioned earlier. We're sorry about the disjointedness of this protocol, this presentation. That's kind of the way we worked. You don't find things in a linear manner. That would be really nice, but we didn't. So this is our crazy wall. And I'll just show you a couple of things. This is a lot to process, and I don't want to spend a lot of time here. But what we did first is we started by organizing our packets by the way they happen. So each one of these little blocks of text is a communication. And what we started doing is we just started spacing things out in the way that made sense to us. So remember we had that 0dB9? This is what Woody was talking about. We Control F for it, and we found it in another part of the packet. And so we used that to create divisions within the packet structure, and that helped us break the fields out outside the packet. Moving on down, so these are communications. So again, 10 was the hello, I'd like to talk to you. 62 was I'm there. 23 was this is the person I actually wanted to talk to. Remember, this was the GID coming along here. Followed by, yep, that's me. Here's the packet, and I got it. Thank you very much. When you have it in this structure, you can see some interesting things, but not everything. One of the neat ones, if I can find it. Yeah, here it is. This was a long message that got sent. And so if you have a very long message, it gives you a high probability of a bit error, which means your packet's going to get dropped. So you chop your messages up to smaller packets so that you have a better chance of getting through. So this is part 1, and this was part 2 of the message. But what really helped was when we looked at it from a different perspective. Let's gather all the transmit announcements on the control channel. Let's gather all of those together and look at them again. And that helped us see more things down here in the packet. All right. So once we started finding that type length data paradigm again, we saw, okay, FB, OF, da-da-da-da-da. Oh, hey, look, there's the Gotenna ID that we found. We Control Left, and that popped out. So within the message, FB, that means this is the Gotenna ID. There's lots of little other things that we didn't particularly understand. Here's your message, 41, 62, 63, that's ABC. And then at the beginning, this one here, the type 3, wraps the entirety of the packet. And so this is my crazy wall. You got to be careful with crazy walls. Enough said. So to break the packet apart, we showed you like all these bytes and your eyes are probably blurry, so were ours. So to make it simple, you've got a packet header at the start of every packet. Optionally, there's a frame that shows up at the end of the packet, which is, again, the type, length, and then some checksum at the end of it. Each frame you can stick together to form a message, and the message has the type length whatever. So if I type a message to you, there's several frames that build together to form some sort of message. Which brings us to this part here.
So as we look at this, what we would like to see versus what we did see versus how things work. Your broadcast messages are meant for everyone. Let's say there's an emergency, you want someone to know where you are, you just send it out, it's not encrypted, everyone can see it. You can also say you're lat long, there's quite a bit to it. It's a great protocol. Again, I'm not slamming Gotenna. I think it's a great thing, and I don't discourage anyone from using them. I just want you to understand the difference between anonymity and privacy and security. They're different elements. Now, in the broadcast, you can see everything from who's sending it to it goes out to everyone. You can see the initials of who's sending the message. You can see GPS coordinates, messages, all that. Now, on the private side, I can still see the sender. But there's actually a little bit more I can see too. Not just the sender, but I can also see who it's going to. Yeah, so early in the conversation, I can see who it's going to and who it's from. How does this bother us? Well, because maybe some of that could be protected a little bit better. You don't have to necessarily give away both ends of the conversation. I want you to think a tour. Do we want everyone to know where we're starting and where we're going? Could be dangerous. So as we move forward and we start looking at this, we start thinking, what would our goals be? What would we like to see? We'd like to see a little less information come out of that. And with that, initially the name of the program was called GODUMP, kind of like Arrow Dump. But then we started realizing, wow, this is a little bit overseen. It sees everything going on. Who's sending something? Who's receiving something? What channel they're going to go to next? It lets us know how big the packet is. So if I know how much information you sent, where it started from, and where it's going to, would that be of any value to anybody? If it is, it is. If it isn't, it isn't. I'm going to leave it at that.
I forgot something really quick.
So now, what we're going to show you is a little bit about how some of the SCAPI plays into this. So you can see, what does it look like if so what we're going to release, Saron, we want to kind of show you a little bit about what it looks like and how we put this into place, going from what we're initially using to SCAPI.
So I'm sure all of you guys in here are familiar with SCAPI, but to explain it a little bit better, just in case anyone doesn't know, it's a Python framework for understanding packets. So you give it a block of data. So I've got this here. I called this variable m, and you feed that into an object, and SCAPI will pull apart the fields as you've told it, and it will let you access them in a really easy programmatic way. So one of the things you can do here is packet.show. And so what you're looking at, right, it was type 45 packet, which if you guys remember, that was here's the data I'm sending to you. So it automatically understands that. It's a message fragment. It pulled apart the payload down here. And it separated that out for us. However, the payload, remember, it's a multiple step thing. And so you might need more sequences or more fragments to make the complete payload. I know for a fact that this one was short. So I'm going to pull it out really quickly. I'm going to do packet.fragment, or you know what? I can't even remember my own code. So we're not going to do this. We're just going to show you Sauron. Whatever.
So from here we're going to move into Sauron. All right. So you're going to see something similar to this soon, because what happened was, in the beautiful mind, he put all this together and he actually has it spit it out, so you have to do zero work. So do you see where it says press enter to quit? That's because right now we're live and we're going to go ahead and just go live with this. Okay, because again, you probably want to see it. What's that? That's right, let's just go live. Then we don't have to remember the code. So, oh, wait a minute. What is that? So Tim just sent a broadcast message over Gotenna. So this would go out to anyone. So if you had a Gotenna, you'd be able to read and decrypt this too. But the simple fact is we now have a listener, a packet sniffer that can listen to all of this and make it happen. Now on top of that,
let me move this up for some people that
can't see it.
Yeah, exactly. I'm going to send another broadcast message.
You got it. They can't see it. There's nothing up there.
Yeah, I know. There's nothing. It just
Okay.
killed again.
Unscheitz's a biscuit. Okay.
Susan's. All right. Sorry, I can't. Good enough.
Spelling errors are okay. Yeah, you're not in any of it.
Oh, come on, Gotenna. Get up there. First the demo guides, right?
Okay. So while he's putting that back up, does anyone in here have a Gotenna? If you do, send a message. Go ahead. What's the worst that happens? Let's go live. Everyone with a Gotenna, launch them as fast as you can. Let's go. Tim does not want this to happen, but I do. Let's see it. Oh, if you're using your phone number, don't do it unless you really want some things to happen. So Tim, you're not paired with anything.
No, that sent the message out. It just didn't show up on the screen.
I told you.
Again, one more time. Yeah, we got bored up. Sorry. Sometimes things crash.
Kids these days. So, hold on. Let me get my Gotenna up.
Go ahead, Woody.
All right. So, here's what we're going to do. We're going to go ahead and look at a couple things. We're going to launch some Gotennas, and we're going to make some things talk and go live with it. Okay. There we go. Now, so, again, if you have a Gotenna, please feel free to send whatever messages you want, and we'll just see what happens randomly. Go.
Scientific progress goes boing. I just did. It's not.
Oh, you're paired. That one right there.
No, that one's my other phone. My
Okay,
phone's
we'll send it.
Hey, Jared, I'm going to send you a private message real quick. I hope you don't mind.
All right, so now he's going to send a message. Jared, is yours up? All right. So we got Jay Boone in the room, which, by the way, if any of you do software-defined radio, like, just amazing work. He's just incredible. So.
Oh, my goodness. Scientific progress going boing. Maybe too many antennas open. One more shot, and then we're going to move on.
Yeah.
Say again?
What radio are you using?
That one.
Are you sure?
One more shot.
It doesn't look up.
Ah, it'll.
No, that's not it. Is anyone jamming any of the MERS channels? Just.
All right, one more shot, and then we're going to move on with the talk. All right, so he got the message.
Use the old code. If this one's not working, use the old code.
We're getting the packets, it's just not working. Sad day. All right, scientific progress goes boing. Give it another shot. If we got more time with
Go again. We don't. We're no, go. Try it again. Okay, so what winds up happening is, wish we had HDMI. Go ahead, push it. Here we go. So we're going to run off the other radio. So when this is working, which typically it was up till earlier, that's why if anyone is jamming MERS, please don't. So what will happen is it'll actually spit out your message. So let me tell you what you're going to be able to see. Who sent the message, who's the message going to, and how large is the message. Oh, wait a minute.
There it is.
Oh, shoot. Can you go ahead and pull that up a little bit?
One more shot.
No, it pulled up. There we go. So now we're up again. So, wait, what is 757-512? Oh, a phone number? So we're using a burner phone up here, and the burner phone's phone number is, although it's not quad zeros at the end, which we've modified that out, you get to see where it came from, who it's going to, and what it means. And you see where it says DEF CON? That's the individual name of the individual who has listed that as their name. So if you said Jeff Wilson, it would say JW. What we did is made a very long name that the first initial of each name spelled out DEF CON. But that's a live demo right there. You're actually able to see it. So,
Do I get this one? So sorry that didn't quite work out the way we hoped it would, but it's a live environment. So the metadata circle, this is like a lame thing that I came up with to try and explain metadata. So there's like 5 different things that are being sent out whenever you transmit packets. Who, when, where, how much, and then the actual content. With cryptography, you can kind of get rid of the content. You can hide that and make it so that people can't see what you're saying. The who, that's a little tricky to hide, because at some point my Gotenna has to say to someone else's Gotenna, I'm talking to you. The cryptographic protocols can compensate for that, but it makes it really tough to program, and it makes what's supposed to be a simple device really complicated. But that being said, who it's going to, we understand why they have that. Who it's coming from, we definitely think that should be encrypted. As far as when, where, and how much, you're not going to get away from transmitting energy. You have to use energy to send a signal. There's no getting out of it. And especially since we're constrained in frequency, we've only got a particular, We've only got a particular bandwidth. We have to put all of our energy in that tiny narrow channel so we can get a long range. And that just shows up like a thumbtack on the waterfall. So everyone's going to know when you transmitted. They're going to know where you transmitted because they were with you when they caught that waveform. And they're also going to know how much got transmitted just by the length. So it's understandable that you can't get away from those things there. Also, it's on a mobile device. I'm not particularly sure that mobile devices are the most secure things ever. I'm not convinced, but that's just me. So we did contact Gotenna and we said, hey, look, we'd like to talk to you guys about this. We think this was maybe perhaps a mistake in your design. And they did come back they were very responsive to us. They were very welcoming of our analysis and our report, and they were thankful for it. And they said, right now, what we're promising our users is encryption. We're not promising them anonymity, right? So they said, it's kind of like an envelope. You can look at the inside of the envelope, or you can look at the outside of the envelope and get to and from, but the inside's encrypted. We didn't really study their cryptography protocol very much because we're not cryptographers, but as far as we can tell, they are encrypting it. Just to wrap up, go for it.
Go ahead and go live demo. We'll pull it up. We'll cover this. Yep. Go ahead. We got 5.
All right, we'll give it a shot.
So, as we wrap this up, we're going to go ahead and just talk a little bit more about this, and we're only going to have a couple questions. Nice. I love seeing the Gotenna traffic that's kicking through here right now. So what we want to be able to tell people is, hey, as you go through and do this, there's a couple key features that are going to be safe that we want you to think about. Do not use your phone number. Why? Well, that is just going to be a bad day. There we go. Now we got it kicking up. So see to and from. Now, the couple things that I want you to realize, Gotenna, I think, is still a great product. If I send an encrypted message to somebody, a couple of things that are going to wind up happening is that you're going to have issues. Those issues are, if you use your phone number, I'm going to see your phone number. If you send, hold on, pull down. Do you see what that's, Tim, do you see right there where it says location? What's that just came across? Somebody just broadcast their actual Latin long. We can see that if they're using broadcast. Even if they're using encrypted, we can see who it came from, who it's going to, and the size of the packet. Anyone in here that does targeting, I think you understand what that means. They were very receptive. They gave us a code that we can use if anyone wants to buy Gotennas. They gave us a discount for DEF CON. We do not work for Gotenna. We are not salesmen for them or anything else, but part of the responsible disclosure was to tell them. So they said, hey, they said, thank you. If anyone wants 15% off, use this code and you can buy their product. I'm a big fan of it, okay? But as you can see, and we did go live. We had some recorded video, but we figured live was better because you guys are a pretty impressive crew. Anytime if you're a person that designs a protocol and you're using command channels, be careful with exposing where you're going to be next, who you're talking to, who you are, and where it's going to go, and the size of the packet. Because if you're a protester, if you're a government person, if you're anyone that uses this, realize if I'm a celebrity and I walk down the street with a protective detail, I have security. If I'm that same celebrity and I disguise myself and I sit on the corner of the street like a homeless person that no one looks at, I now have anonymity, but I no longer have security. Just like the celebrity surrounded by a bodyguard detail doesn't have anonymity. The two are not always the same. And that's one of the biggest things we want you to take away from this talk. Security is not anonymity, and anonymity is not security. But each can be used to protect in certain and individual ways. Further work.
So we have a lot of work that's still not done. We haven't found the checksum yet. It's kind of embarrassing. We don't know how the cryptography works. If you're a cryptographer, we're going to be putting this online in a couple days. So we'd love your input. We haven't done anything with group chat or emergency broadcasts or any of these like millions of unknown fields. So we've got a lot of work to do still. So I guess we've got about 5 minutes left. Some things that we wanted to talk about is just what worked in this project. If you're new to the security research field, you're coming into this, there's some basic skills that are helpful. The first is know your tools. Know cut, grep, sort, unique, gnome calculator, gedit. We can have the fancy tools with the $100 equipment, but if you can't use these basic tools, what uses your equipment? Just like Zero was saying earlier on. Also, know your formats: integers, chars, shorts, floats, hexadecimal, binary, strings. Know how to convert between the other, move it around. Yep, we're finishing up. We're nearly done. Automation. You can do this with some of the tools. What's the name? Yeah, like D-Spectrum, but it's not going to get you too far. You need automation.
So, again, in conclusion, we appreciate your time. Understand how people communicate. Know human patterns. Try before you pry. Sometimes you might get that serial port before you have to solder into something. Change one thing at a time. And if nothing else, if you're a new person out there who's never had a chance to speak or be in front of a crowd, submit to the Wireless Village, because these guys are amazing. They'll put you out there and they'll let you do it, and they're just good people. Thank you so much for everything you've done. These are our Twitter handles.